starts our class. Okay, can all of you hear me?
Yes.
Okay, thank you.
Yeah.
Can
Okay, today we will start with a new topic, which is integration. Okay, so before we start with the method on how to integrate, let's um, let's see the overview of the area problem, which is obviously related to the integrations. Okay, so if you have like a region, okay, when I say region, it means that it is enclosed by boundaries. Okay, so the boundaries are considered as, let's say, this function here, y equal to f of x. Okay, so you can have any function y equal to f of x, and then let's say it is restricted, okay, from a up to b. Okay, it could be any values. Okay, these values for a and b could be any values. Okay, and then the area under the graph, okay, under this graph y equal to f of x. Okay, so this is y and this is x. Okay, up to this x-axis, up to here, okay, is actually represent the integration. Okay, so the integration is from x equal to a up to x equal to b. So it is from here a up to b, and then we integrate with respect to x. Okay, the difference here, b up to a or a up to b here represent the x-axis. So the differentiation is with respect to x-axis. So it is dx. Okay, and then the integration is the area under the curve y equal to fx. So we integrate with respect to the function f of x. Okay, so this is the definition of the integration. It is the values of the integration. Sorry, the values of the area under the curve or the graph. Okay, and then it is not always easy for us to integrate. Okay, it might be easy for a very simple function like fx equal to 2x. Okay, dx x, let's say, is from 1 up to 2. You know that if we integrate this, I think from the previous knowledge, you already know that this one, okay, if you integrate this function analytically, you will get 2x squared over 2, and then it is from x equal to 1 up to x equal to 2. So this is how you integrate for easy functions, but it is not always that easy. Sometimes the function is difficult for you to get the analytical solution. So analytical solutions means this one, the integration of 2x, you will get 2x squared divided by 2. So this is the analytical solution when you integrate. Okay, but for a very complicated function, you may not be able to integrate this analytically. So what you do is normally to find the area under the curve numerically. When I say numerically, means that by using approximation. Okay, when I say numerically, it's basically approximation. Approximations means that the value is not exactly the same as the analytical values that we got, but might be close to. Okay, we are hoping that our numerical values will be close to the analytical solution. Okay, is it clear? So we want it to be as close as possible to the analytical solution. Okay. Okay. Let's see this example here. Is this an example? Okay, this one. Y is equal to x squared. So the function is not difficult for you to integrate analytically. If you to integrate this, if you want to find the area under the curve for this function x squared, okay, with respect to the x, and here x is equal to 0 up to x equal to 1. Sorry, 0 up to 1. If you integrate this, you will get x cubed divided by 3. X is from 0 up to 1, which give you 1/3. So this is the solution that you obtain analytically. So we want to show the solution if we impose the numerical approach. Okay, so for the numerical approach here is we will subdivide this interval from 0 up to 1 to several rectangles. Okay, we will subdivide this into several rectangles. In this case, how many rectangles that they consider? For example, if we take n equal to 4, so let's take n equal to 4. Okay, we will take it the rectangle which have equal distance length. Okay, so when n is equal to 4, it means that the length for each of the rectangles is 0.25. Okay, so we subdivide it into 4 parts. Okay, so each of them will be 0.25 because it's from here up to here will be 1. Okay, so this one will be 0.5 and here will be 0.75. So each of this length will take 0.25. Okay, and then there's several ways on how to represent the rectangles. Okay, one way is to represent the rectangle so that we take the right endpoint or left endpoints or centered. Okay, centered endpoints. Okay, so for this one, if we count the point or the collocation points or the nodes point here, it will be 5. So you start from here, 1, 2, 3, 4, 5, isn't it? Altogether with 0 and 1. These 3 points in the middle, interior to the region, okay, as well as on the border, which is 0 and 1. So there are 5 altogether. Okay, so for the right endpoint, okay, so here they consider right endpoint. For the right endpoints, the first point will be the right endpoints. So between this one and this one, the right endpoint is this one. So we neglect x equal to 0 as the node points. Okay, so the rectangle will start from this right endpoints, and then for this rectangles here, the right endpoint will be this one. Okay, so we consider this one to draw the vertical lines in order to draw the rectangles. So it will be something like this. And for this one as well, the right endpoint is this one here. So we draw it like that. Okay, for this rectangle, the last rectangle here, the right endpoint is 1 here. Okay, so we consider this one. So we draw it from the right endpoints up to this part here. So this is the rectangles for the right endpoints. Okay. So there are several ways. As I said before. Okay. Let's go to another ways. One note. Okay, this one. Okay. So as before, you have y equal to x squared. So this is y equal to x squared, and you have 0 up to 1. So this is your x, and this is your y. Okay, and then you start divide the interval into 4 equal distance rectangles. Okay, and then let's say here you consider left hand point instead of right hand point. Okay, consider left hand points. So for the first rectangle, the first endpoint is this one. So your rectangles for the first one is nothing. Okay, because you consider the first one, it is 0. So the first one will just flat on the x-axis. Okay, for the second one, okay, for the second rectangles, the left hand points is this one. So it will be starting from this, and you draw the horizontal rectangles. For the third one will be something like this, and for the fourth one will be like that. Okay, so this is the approximation. You won't get the exact values as the analytical solution. The analytical solution is 1/3. You will get if you think as logical ways, it will actually give you less than 1/3. Okay, because you have hollow regions over here. Okay, and for the previous one, for the right endpoints here, you will have additional region, and this one will exceed 1/3. It will exceed 1/3 instead of less than 1/3. Okay, and then we obviously have another ways, which is by using centered points. Okay, so let's say you have y equal to x squared. Okay, and then it's subdivide into 4. In this case, you take n equal to 4. Obviously, if you want it to be very close to the exact solution, you have to take n tends to infinity. When n tends to infinity, then it will be close to the exact solution, which is very accurate. Okay. Okay. For the centered one, it means that this will be the centered. So this is equal distance. So here will be the centered. So we draw the lines which corresponds to f of this centered point. Okay, and this is the centered. So we draw the line that corresponds to this exact these values of f of this centered point, and this one as well. Okay, this one as well, and for this one as well. So this is basically the approximation that we might be considering. So for this one, it is centered. Okay, is it okay with all the three methods? Okay, I hope this is okay. Okay, let's go to the to these rectangles here. When we say approximation and we have several rectangles, the purpose is to find the region. And since we subdivide it into rectangles, it means that the area for the rectangles will be what? Will be the length multiplied with the height, isn't it? You will have the length, the length of the base of the rectangles. You multiply with the height of the rectangles. So let's say for this one, you will have this height here. and then you have to multiply with the length of the base. And since the length of the base is equally distance for each of the rectangles, it is just 0.25 if you have if you take n equal to 4. Okay, and then what about the height? So this is 0.25, so the base will be 0.25. There's nothing special. But for the height, you know that for the right hand points, it corresponds to the right hand points. So for this one, 0.75 and 1. You consider the 1, isn't it? And what about the height? I mean the values of this one. So this is f of 1, isn't it? F of 1 is equal to, the function is y equal to x squared. So f of 1 will be 1 squared, which give you 1. So for the height, for this first rectangles here, okay, for the tallest rectangle here will be 1. And then for this one, for the second one, okay, the right endpoint is 0.75. The height will be what? 0.75 squared. It corresponds to the function. If the function is y equal to x cubed, then you have to write here, let's say 0.75 cubed. In this case, it is squared, 0.75 squared. Okay, and then this one as well. Okay, and then you add up, and then after that you sum up all the area for each of the rectangles. Okay. And then mine is what? Someone write the if you have problem and give me the that sound, please just watch the recorded versions. I'm afraid that it will disturb your friends. Okay. Okay, and then here an is 1 over n squared. So 1 over n squared, in this case n is equal to 4, so 1 over 4, which is 0.25 squared will is actually representing the height of each of these. Okay, and for this one, 2 divided by n squared. Okay, so this is for the second one. Okay, 2 divided by 1, which gave you, sorry, 4. 2 divided by 4, which give you 1/2. So you will get 0.5 here. 0.5 squared represent the height of the second rectangles. Okay, for this rectangle here. And then for the third one, 3 divided by 4, okay, it gives you 0.75 squared. Okay, this represent the height of this one, of these rectangles here. Okay, and lastly it is 1. The last one will be 1. Okay, 1, or in this case it is actually n divided by n. Okay, n divided by n, or 4 divided by 4. Okay, squared. Okay, and then you multiply with the length of the base. So in this case, the length of the base is 1 over n, or in our example here, it is 1 over 4. Okay, it is 0.25. So this is the basic formula, okay, or the general formula for the general n. Okay, and then you can specify the value of n later on. Okay, and then for n equal to 4, generalized from here, it will be this one. Okay, and if you sum up, since the purpose is to find the summation of each of the rectangles, if you sum up, you will get 0.46875. As I mentioned before, we already expect expect that the value will exceed 1/3 because we see that each of the rectangles have additional extra region here. So it is 0.4687, which exceed 1/3. Okay, the 1/3 is obtained from the analytical solution. Okay, and then obviously when we let n tends to infinity, you will be close to 1/3 lah. It will be 1/3. Okay, so this table here represents the values of the summation for the area of the rectangles for n equal to 4, n equal to 10, n equal to 100, and so on. As we see, as n is getting closer to infinity, then it will be close to 1/3. Okay. Next one is the antiderivative methods for finding areas. So let's look at example 1. For each of the function f, find the area a of x between the graph of f and the interval a comma x, okay, is equal to -1x, and find the derivative a prime of this area function. So a is equal to fx equal to, sorry, a is for fx equal to 2, okay. And then let's look at the figure. So y equal to 2 is the horizontal line which cross or pass through y equal to 2. So this is y equal to 2. Okay, you have a straight line here. And then the area under the curve, okay, for y equal to 2, and then you integrate with respect to x, okay. And in this case, for the questions, you have a x is equal to -1 up to x, okay. So it means that your initial points on the x-axis will be what? It is -1 up to x, okay. So it will be -1 up to, for the upper parts it will take x, okay, in -1 up to x. So -1 is over here, is before the origin 0, 0. Okay, let's say start from here, and then it's up to x. So this x here is a variable which can take any values, okay. If you see the area for this for the area under the curve for this function y equal to 2, you don't have to subdivide it into several rectangles like before, because it is not difficult for you to approximate. You know that the area under the curve in this case is just the area for the rectangles itself, for n rectangle itself, which take the height equal to 2. So this is the height, which is equal to 2, okay. And then the base will be x minus -1 or x plus 1. So the area function a of x, when I say area function, it means that it still depends on the variable x. X can take whatever values. We don't write it as a. Okay, a of x is still a function of x. Okay, a of x here is equal to 1/2. This is from different questions. We want it for this one. So a of x for the first one is what? The height is 2 multiplied with x plus x. Sorry, x plus 1. This is x plus 1. That's it. I think that's will be the solution. Yeah, 2 multiplied with x plus 1. Okay. So if you differentiate this area function a prime, you will get equal to 2, which is the original function f. Okay, and then for the second one, somehow it says that fx is equal to x plus 2, okay, and then obviously the x starts from -1 up to x here. The interval here start from -1 up to x, okay. So the function is x plus 1. It is a linear function, okay. When I say y equal to x plus 1, it means that it is a linear function, okay. It is a linear function that intersect at y equal to 1, isn't it? You already know the line. I'm not sure. The equation for the straight line, which is y equal to mx plus c. The c here represent the y-intercept. Okay, so the y-intercept will be 1, and then somehow you will have here the slope for the straight line is equal to 1, isn't it? So it means that our x-intercept will be equal to -1. So this is the line, okay, that represent the function. And then like before, it start from -1 up to x. Okay, so if we look at closely to the region, we know that it represent a triangle. Okay, like in the previous example, it present rectangles. Okay, so for the triangle, we have different formulas for the area, which is 1/2 multiplied with the height multiplied with the base. Okay, so for the base, you know that it is x plus 1, and then for the height here, this is the x. Okay, so for the interval, x is the maximum. Okay, even though it is just a variable, we know that it is x. If the function is given by x plus 1, it means that the height will be x plus 1 as well. Okay, if this one is equal to x here is equal to 2, then the height here you have to substitute 2 plus 1. It will be 3 over here. But this is still a variable, which is x. So the height here stays as x plus 1. Okay, so the formula will be ax equal to 1/2 multiplied with the base, which is x plus 1, and then you multiply with the height, which is x plus 1, and then you simplify this, you get x squared over 2 plus x plus 1/2. And then if you differentiate, you will get this function here, you will get x plus 1, which is the original function fx. Okay, and then for the question C and D, I think you can do it at home. Okay, I think that's it. Okay, let's continue with the indefinite integral. So for the integral, you have two types. One is definite integrals, another one is indefinite. Okay, so the difference is this word here. So indefinite means you don't have the upper and the lower limits. So this is the integration sign, and let's say you differentiate with respect to x. Okay, this is the function fx. Okay, x is equal to something. Let's say x is equal to a, x is equal to b. For this case, the integration, this integral here does has the upper and the lower limits. Okay, when I say it has the upper and the lower limits, it means that the result or the solution will be finite. Okay, will be defined. You can get the solution, you can get the values for this integration. So this integration here is called definite. But if the limits, the upper and the lower limits are missing, then it is called indefinite. So the solutions for the indefinite integral will be in terms of function instead of a solution in terms of real values or whatever values, let's say complex values or whatever. Okay, it won't give you in terms of function anymore. Okay, but for the indefinite, it will still be in terms of function. Okay, I think you can read that. Okay, you can go one by one from this. It's just revision. Okay, I think I'm sure you already know about this. Okay, this one. This is just power rules. X to the power of 3. If you differentiate, you will get 3x squared. And then for the integration of 3x squared, you will get x cubed. So basically, they are very close to the to what we got from different sessions. It's just the inverse operation. Okay, and x cubed here, we got 3x squared is from the power rules. Okay, from the power rules. It might not be difficult for some function like involving power rules, but when it's involved trigonometric, then some of the function it needs you to memorize a bit. Okay, like maybe before you know that tangent t, if you differentiate with respect to t, you will get secant squared t. Okay, but it's not always easy for you to get it instantly for the integration of secant squared t if you never memorize this. Okay, because I'm always teaching you, if you want to differentiate, if you don't know on how to differentiate, if you don't want to memorize, the thing that you should consider is to represent the tangent t here in terms of quotient, right? The tangent t, you represent it in terms of sine sine t divided by cos t, and then you do it, you differentiate it by using quotient rule, then obviously you will get secant squared t. So that is what I have teaching you before, right? But in this integration parts here, when we study about integrations, you still have to remember. Okay, what is the integration of secant squared t or something like that. For the power methods is quite obvious, and the tables that you might want to look at is this one, this table 5.2.1. Okay, and then that's it. It's not some of the functions, the function which are already familiar. Okay, but some of them you might want to study a bit. Okay, and then this is the theorems. If you have a constant under the integration sign, c here, you can always take out the c, and then if you have additional function, you can always segregate. For the minus as well, you can always segregate the two. Okay, but when it's involved quotient as well as multiplication, you cannot segregate. Okay, it's only available for the additional and subtraction. Okay, and constant as well. Okay, for the multiplication and quotient, you cannot simply segregate each of the term. Is it clear?
Yes, clear.
Okay, good. Okay, next, example 2, evaluate integration 4 cos dx. So for this one, the 4 is a constant, you can always take out. Okay, like in the previous theorems, you can always take out from the integration sign. So what is left inside or under the integration sign will be cos x. Okay, you integrate cos x, you will get sine x. Okay, so the final answer will be 4 sine x plus c. For the indefinite integrals, you should always have this plus c. Okay, for the definite, you will get the exact values. Okay, for the indefinite, you will have a function. So this is considered as function in terms of x. 4 sine x is a function still in terms of x, and then you will have additional constant plus c. Okay, and then for b, x plus x squared, so this is plus here, so you can always segregate. Okay, so you segregate it, integration x dx plus integration of x squared dx. Okay, you integrate this. This is just power rules. Again, it will give you x squared divided by 2, okay, plus x cubed divided by 3, and then you will have plus c. Okay, I think that's it. For the other examples, I'm sure you can do it at home. Okay, I think this one is easy. Okay, I will leave it for you to do it at home. What about example 4? Example 4, cos x sine squared x dx. Okay, so when it involves trigonometrics, for a new learner, it might be quite it looks scary. Okay, it looks scary, but it's nothing actually. You have to do lots of exercises to be familiar with all this function. Okay, so for this one here, for cos x sine squared x, what they did in this solution here is they simplified this so that it is 1 over sine x, and then you have another one which is cos x sine x. Okay, so the new function will be cosecant x multiplied with cotangent x. Okay, and then you look at the table. Okay, from the table, okay, which one of it? Then this one, right? So the answer will be negative cosecant x. Okay, so the answer will be negative cosecant x plus c. Okay, after somehow they simplified that. Okay, is there any other methods on how to solve these integrals? What do you think? Do you think there's another or maybe a better way on how to solve these integrals? What about substitution? Is it possible? Let's try substitutions. Okay, so cos x sine squared x. Cos x divided by sine squared x, and you integrate with respect to dx. With respect to x here, so for the substitution, let's take u equal to sine x. Okay, so your du, you differentiate u with respect to x, you will get du dx equal to cos x. Okay, and then for this one, it will be cos x divided by u squared. Okay, for this one, dx is from here. Dx will be du divided by cos x. Okay, so we change these integrations variables so that it is in terms of u. Okay, so our dx here can be represented as du divided by cos x. So du divided by cos x. Okay, so we see that this function here, this cos x, can be cancelled out. So what is left will be just 1 over u squared. So this is u to the power of negative 2 du. So it looks much easier for you to apply power rules. Okay, so integration of u to the power of negative 2, you integrate respect to u. This one will give you negative 2 plus 1 divided by what? Negative 2 plus 1 and then plus c, isn't it? So it will give you what? U negative 1 divided by negative 1 plus c, or it can also be written as negative 1 over u plus c, and then you change everything back to in terms of x. It will give you negative 1 over sine x plus c. So this is the this is the exact solution that we get when we apply the substitution method. Okay, and if we compare, this is negative 1 over sine x. If we compare with the solution that they get, it is negative cosecant of x. Cosecant is 1 over sine. Okay, so they are just the same. Negative 1 over sine x plus c. They will provide the same solution. Okay, you can use you can try whatever methods that you are comfortable with. Okay, next one. Okay. For B and C, I think there's nothing. For B, there's nothing difficult. But for C here, what about for C? X squared divided by x squared plus 1. Okay, so for the x squared divided by x squared plus 1, okay, for the substitution, it's not easy for you to apply substitution because this is in terms of power 2, and for the numerator is also involve variable with power 2 as well. Okay, so I think for the substitution methods it's not suitable. Okay, so what they did here is they create a new constant plus 1, and then they have minus 1 as well, which is equal to x squared. So we know that x squared is always equal to x squared minus 1, and then you have plus 1. Okay, so for x squared plus 1, you divide with x squared plus 1, this one will give 1. And then for the second one is negative 1 divided by x squared plus 1. Okay, and then for the second term here, for the first term, it is fine. It's just power rules. You integrate 1, you will get x, isn't it? But then for the second term, this can be obtained from the table. Okay, 1 over x squared plus 1 for the integration will give you arctangent. Okay, will give you arctangent for this one. Okay, arctangent. You differentiate arctangent of x, you will get 1 over 1 plus x squared. You integrate 1 over 1 plus x squared, you will get arctangent x plus c. So we will use that one. Okay, so that's why you get negative arctangent x plus c. Okay, so that's it. That's it. Yeah. Then next one will be integration by substitution. Before that, I think it's better if we take like 5 minutes break.
Thank you, Doctor.
Okay, so let's continue. Before that, if any of you know how to switch off the beep beep sound whenever your friend join this meeting room or leave the meeting rooms, please let me know, okay? Because I'm very irritated with the sound, especially when you are teaching to all of the students, and somehow the sound um, keep on disturbing me. Okay. But whatever it is, let's just continue. But if any of you know on how to do that, please let me know. Okay. Um, so for the next method, or for the next subsection, will be integration by substitution. I've mentioned this in the previous example, I think we even solved one of the example by using substitution. So substitution is a method that you always try first whenever you want to solve an integration. Okay, we don't always go to the integration part by parts. Okay, uh, for the first try. Okay, we always try substitution before it. But if the substitution fail, then we go to maybe we have to go to the next method. Okay, but we don't try integration by parts for your first try. Okay, you normally try to solve it by substitution, or maybe for the first one, maybe you look at the function. Either you can use power rules, or you can see you can solve it just based on the table or something like that. And then if you can't, then you go to the integration by substitution. And then if it still fail, then it will you might want to try other methods like substitution trigonometric substitutions, or maybe integration by parts. Okay, for this one, okay, example 1, x squared plus 1 to the power of 50 to x. Okay, so if we look at the example, you know that you can do the substitution. Why is that? It's because the substitution involves differentiating. Okay, you differentiate the function. Okay, and then the function that you differentiate, the aim of it is to cancel out with the original function under the integration under the integration sign. Okay, so for this one, x squared plus 1, you know that if you differentiate this, you will get 2x. And obviously the 2x you can cancel out with the existing function under the integration sign. Okay, so from that, you know that you can solve by using substitution. So let's try it. So for this one, the u, or the function that you want to substitute, is normally the function under the bracket, inside the bracket. Okay, so that is the key. Okay, so in this case, the u will be x squared plus 1. Okay, so you differentiate this, you get what? You get 2x, okay, dx, okay, and then you want to replace the dx here in terms of du, so makes dx as the subject, so your dx will be du divided by 2x. Okay, so from here it can be written as what? So the original one, so the substitution one here will be u to the power of 50, so 50 still there. Okay, and then you have 2x. Okay, and then for the dx, you replace with du divided by 2x, so you will get du divided by 2x. Okay, the 2x will be cancelled out, so u to the power of 50 du. Okay, so if you look at the new function here, the x is 100% eliminated. Okay, you can somehow eliminate all the function x. Okay, so that is the purpose. You want only the u, the new function in terms of u exists under the integration sign without the original variable x. Okay, if the x is still there, you cannot cancel out, then it means that your substitution method failed. You have to try another method. Okay, next. sine x plus 9 dx. So you know the integration of sine x with respect to x, you get what? You get negative cos x. So that is what you know. Okay, integration of sine x, it give you negative cos x. So this is something that you already know. Okay, but you never know on how to integrate sine x plus 9. This is not something which is obvious from the first sight. Okay, but it's okay, you can apply substitution rule. As I mentioned before, the substitution u is normally interior to the bracket, to this bracket here. So the u is taken to be x plus 9. Okay, so you differentiate u with respect to x, you get du equal to dx. So x as the subject is equal to du. Okay, and then you replace everything here, which is originally in terms of x. You want to change it so that it's only involve u instead of x. Okay, so this one will be sine u, and then the dx here will stay as du. So you integrate sine u with respect to u, it will give you negative cos x. Okay, negative cos u. Okay, because you integrate with respect to u, and you cannot stop there. You have to change everything to the variable x. Okay, so it will give you negative cos x plus 9, and then this is the indefinite integration, so that's why you have to add plus c. Okay, so that's it. And then for the next example, x minus 8 to the power of 23. So the u that you want to take will be interior to the bracket, as I mentioned before. So it will be u equal to x minus 8. Okay, so the du will be equal to 1. So the dx will be equal, I think this is not correct. This is this is correct. So du is equal to dx, okay? And then u to the power of the 23 du, you just use power rules. You get u to the power of 24 divided by 4 plus. And this is okay. And then for example 3, cos 5x. So can you guess what will be the u?
Negative 5x.
Yeah, u will be 5x, okay? And then obviously you still have to change the dx here to get the positions of u. Okay, please switch off your what is this? What is this one? Mohammed Firdaus. Cannot control until why? Please make sure you stay focused during my class and take note. Sorry, at least observe your own WebEx account, and please don't make sure that it doesn't unmute, because it's too difficult for me to unmute your. I can control, but when you have to teach, it's not easy for you to control the setting and everything, you see, and it's quite I don't know, but I'm not in the mood when some of you disturb me. Okay, I'm not in the mood to teach. It makes me feel down, okay? Because I know that some of you doesn't even pay attention, okay? Maybe you just make sure that you join the meeting and make sure that the attendance is there, like that, okay? But whatever it is, I still have to continue our class. You see, I have to attend our class even though it is on Saturday, okay? Because I want to combine all of you together. But still, I need to come to my office during a weekend. Okay, I made some sacrifice. And you have to appreciate that. Okay, and I appreciate that you can join me during Saturday. Okay, during your weekends on Saturday. But please be considerate. Okay, especially yeah, I think I don't have anything to say. But next time, please make sure that you don't disturb your friend. Okay. I think that's it. All of them can. What about example 9? T to the power of 4, 3 minus 5t to the power of 5 to the power of 1/3. So this is cube root. Cube root is just to the power of 1/3. Okay. So for the u, if you want to try substitution, the u, when it involve square root or cube root like this, you can always try the u that represent the function under the square root of the cube root. So the u here will be 3 minus 5t to the power of 5. Okay, and then you differentiate this, you get what? You get negative 25 t to the power of 4. Okay, so du is equal to negative 25 t to the power of 4 dt. So this is what you get when you differentiate. And then what? And then integration t to the power of 4, and then for this one it will be u, okay, to the power of 1/3 to the power of 1/3, and then you have dt. So dt is this one. You make dt as the subject, you will get du over negative 25 t to the power of 4. So this t to the power of 4 can cancel out with this one. Okay, so what is left is just the constant 24. The constant is not something that you should be afraid of. A constant can always be taken out from the integration sign. Okay, you don't have to be afraid of that constant. So the function which is left here is just u to the power of 1/3, which only requires power method. Okay, so u to the power of 1/3 plus 1 divided by 1/3 plus 1. Okay, and then it's obviously still give you 1 over negative 25 over here, and then you have plus c. Okay, I think that's it. Just simplify this, and then change back to t, change back so that it's still in terms of t. So the u is 3 minus 5t squared substitute it again over here, okay, and then you will get the same answer. That's it. And then all the example that we have looked in the previous lecture is very obvious, okay. It's very obvious, it's so easy that from the first glance you know that the substitution methods can solve the integrations, but it could be that you will have a function which is less apparent substitution, which require less apparent substitutions. So let's look at example 11 here. So x squared multiply with square root of x minus 1, okay. So if you want to do the normal substitution, you might see that you might say that the substitution u is normally for those under the square root sign, like I've said before. So you might want to choose u equal to x minus 1, okay, but it doesn't solve this problem. Why I said that is because if you differentiate this, you will get du is equal to dx. Then what? Here will be what? Will be x squared, and then this one will be u to the power of 1/2. Sorry, yeah, it will be to the power of 1/2. This one x squared, and then dx is du, okay. So if you look at here, the x will stays. The purpose of doing substitution methods is you want to change everything in terms of a new function or a new variable, which is in our case it is u, okay. If you look at here, the x still there. So how do you eliminate the x? Okay, so you know that our u is equal to x minus 1, okay, from the first substitutions, okay. So if we want to get rid of this x squared, we want to transform this x squared so that it is in terms of u. Okay, so how do we transform it so that it is in terms of u? So your u plus 1 is equal to x. So x squared will be equal to u plus 1 squared. So this is the key. You want to replace this x squared here so that it is u plus 1 squared. Okay, so once you replace this so that it is u plus 1 squared, you can expand that, okay, and you get u squared plus 2u plus 1, and then for this part here it stays as square root of u or u to the power of 1/2, and then you can combine this, or you can multiply each of the components. So you get u to the power of 5 divided by 2 plus 2u to the power of 3 divided by 2, and then u to the power of 1/2 du. And then for each of the term now can be solved by using a power method. Okay, power method, just power methods. So that's it. It's not difficult. Okay, but if you, without using substitution, you cannot combine. You cannot combine. Like this one, it can combine because this part here is just u to the power of 1/2. Okay, or there's only one component under the square root sign. Okay, there's only one component under the square root or cube root sign. In this case, it is square root sign. But in this case here, you have x minus 1. If you have x minus 1, how do you combine or with the x squared? You cannot. Okay, so the key is to make the variables under this cube root or square root sign, so that is only involve variables. Make it easy, easier recorded it in this solution. So that's it. And then for the example 13, of one of these intention of after a while, it's always happening that after a while, my uh, my own drawing tablets is not functioning. After 1 hours after we start our class, I'm not sure why. Okay. I cannot write it on the on the notes now. I cannot use the drawing tablet. I think that's it. Let's just start our class now. Okay. So, thank you very much for being here again. That's it. Okay. That's it. Thank you very much.